The Digital Equipment Computer Users Society presents this live recording from the 1993 Spring DECUS Symposium held June 5 through 11 at the Georgia World Congress Center in Atlanta, Georgia. And now to our program.
VS060, MUTEX weights and resource weights and MUTEX in the OpenVMS operating system. And this session is given by David Caffey, a consultant out of Dallas, for the Montagan Software Concepts. I probably butchered the name.
That's close.
Montagar. Try it again.
Okay, those of you who don't have session notes, I'll put this up again later. They're in the, I believe they're in demand print. They're also in the session notes you can buy in the bookstore. Or if you don't want to do that, the PostScript version of this is available off my file server at fileserver@montagar.com. Feel free to pull them off there. Also, for my other session, which is tomorrow, my loadable images, you can get those too. Beat the rush. Okay, what we're basically going to talk about is resource weights. Probably a few of you in here have had a resource weight or two and don't like them, but we also need to find out kind of what these things are so we have a better understanding of where they come from, what causes them, so we can get rid of them if we decide we don't like them. But they're not always necessarily a bad thing. So we're also going to discuss resource weights, and also very closely related to resource weights are MUTEXs. They share a lot of the same type of data structures and some of the accessing of them, the way they're stored and stuff. Also, we'll go through the R-waste causes and descriptions. I'm sure there's a few of you that have actually seen a process go into R-waste. No hands. No one's seen it. Just me. And the ones, if you have seen, probably really like to be in R-waste. So we're going to discuss those and probably why they're stuck in R-waste. Also using SDA to determine why they're in R-waste. Once we have a better idea of what R-waste and some of the other resource weights and MUTEXs are, we can go in and start looking around at data structures and figuring out exactly why the process is in the state it's in, and, of course, following on from that, finding out how to break processes out of it, should they get stuck. This is real nice for you people that really don't like to reboot your machine, especially production machines, just because one process gets wedged. And then we're also going to go through a couple of little brute force approaches. Yes, reboot is in there. Sometimes you just got it. Resource weight is a format of a MUTEX, a mutual exclusion semaphore within the OpenVMS system. Mutual exclusion is kind of what it sounds. Mutually exclude everyone else from accessing a particular region, so you're the only one in there. Some of the MUTEXs are also read sharing, so multiple readers can gain access, but no writers can until all the readers have gone away. Resource weights are also a set of events that will suspend a process until a later time that something becomes available. Either the MUTEX becomes available, selected resources that have been flagged have become available, and you can use that to thread some of the processes. The reason why it's done through a MUTEX is because a lot of them tend to be a specific module oriented, such as logical names or whatever. You don't want to sit around and spin around at high IPL trying to guard some large data structure you may be spending some serious time on, because it's going to keep you from processing things like IOs that other people might consider to be rather important. So a lot of this activity, even though it is kernel mode, is also done at very low IPL, so it doesn't affect any other processing. MUTEXs and resource weights, common misbelief is that they are evil. Actually, they're very good. The common use of some of the resource weights and MUTEXs is a form of flow control. I've seen several processes that have set themselves up explicitly to consume all the resources that they've been quoted to try to perform their operations as fast and as furiously as possible. What this has allowed them to do is queue up as many IOs as they can, take up as much buffer limit as they can. And what will end up happening is they will always go into R-waste. They'll also be doing lots of other activity. R-waste is just a way of saying, okay, I've gone in and wasted all my resources, so here I am doing whatever, as much as I can. Real early, before they came up with spin locks and some of the other fun stuff, excuse me, They had mutexes. Mutexes is a synchronization technique where you, using a lock type principle such as NQ and DQ, you assert to the system that I want to access a protected resource. While I have that lock or that mutex on that protected resource, no one else can touch it unless it's a read lock except for me. I have complete control over it. Also, I'm at low IPL, so device interrupts, rescheduling interrupts, and things like that can occur without it, so these high priority type things can still happen, and this is considered more of a lower priority type of a thing. MUTEX is a very simple data structure. It's just 32 bits, a standard long word in the executive. You can also see some more information about it in the Book of Ruth, sometimes known as the VMS Internals and Data Structures Manual. It's in chapter 8.5 on page 196, or in the censored, but of course censored we now know what that means, the Alpha Internals and Data Structures Manual, 9.7, page 950. Here's a list of some of the mutexes that you will find in OpenVMS. Let's see, get that up a little higher. Logical name mutex. If you're going to be scanning through the logical names, you don't want to lock yourself at high IPL for that, because the resource hash tables and things like that may be fairly timely to go through, so that is protected by mutex. There are some places within the I/O database which are protected by mutexes. Line printer drivers and a few other data structures are mutex protected. Common event flags, CPUs, page done, global section descriptors all have their own mutexes as well. CIA, no, we're sorry, this is not some federal agency. This is the Cumulative Intrusion Analysis. Well, since they had the KGB with the key grant block, they stretched a lot to get that acronym down right. What that one is if you've ever done a show intrusion to see what processes have been locked out of the system because they've exceeded number of password failures or whatever, that is the mutex that controls the list with the queue for that particular data structure, so that only certain people in a controlled fashion gain access to that data structure, such as the security audit, delete/intrusion, show/intrusion. Also, an important mutex is the base image mutex. This base image mutex is used to control loading images, such as you can find out on my talk tomorrow, I believe at 3 o'clock in Ballroom 4 on loadable executive images. Don't mind plugging my own stuff. We all like to do that. The base image mutex is used to protect the loader data structure queue, which keeps track of all the images that comprise VMS, such as RMS, process scheduling, I/O routines, and all the other things if you do a show or a show/exec within SDA. MUTEX long word is manipulated through basically 3 routines. There's actually 3 more which are used through internal calls within the executive itself, but typically the ones that are seen commonly are the sched $lockr, lockw, and unlock. Lockr asserts a read lock on a mutex, again allowing multiple readers to go off and examine a particular data structure in a protected fashion, knowing that the data structure is not going to change unexpectedly out from underneath them. The lockw asserts that I will want to change this data structure or queues or whatever, and I want to make sure that all the readers are out of it before I come in. Mutex is a long word divided up into 2 fields. The first field is the owner count. That owner count keeps track of how many processes, which locks or mutexes are typically owned by a process, unlike IPLs, which typically assert ownership by the entire operating system of a particular resource. The owner count keeps track of how many processes are currently accessing that mutex. It's initialized to -1, so you'll always see all F's in that thing, in that data structure normally. But as the ownership goes up, it'll go up to 0, 1 as more readers get in. There's also bit 16, which is the write in progress or write pending status bit. If a writer comes in, the first thing it wants to do is to set that bit. It does a branch on bit set and set interlock. If that bit is set, when it's trying to set it, then it knows there's another writer in the queue, and it goes and puts itself into an MWait state and waits for a sched $unlock call from somebody to go ahead and key that it can be successfully awakened and make another shot at the mutex. Also, if the owner count is non-zero, we'll also have to wait until that decrements to negative before we go off and try to access or allow access to any writers to the queue. Related data structures in the process control block, PCB, there's a mutex count. That is a count of the number of mutexes a current process owns. It's possible for a process to own many mutexes, kind of like with the spin locks that you have. You can have a nesting of the spin locks available. Also, the event flag wait mask is a very important data structure. Normally, it keeps track of what event flag or the mask of the event flags you're waiting for with the wait for event flag system service. If you're in a MUTEX state, this field is also used to keep track of what the address of the MUTEX you're located at. If you do an SDA, do a show process, you'll typically see an 8 big number, whatever, inside that field if you're at a MUTEX. If you're not at a MUTEX, maybe a resource wait, in which case that would actually be another value, and we'll go into that later. Here's a code example taken out of some code that I have that goes off and plays in the intrusion analysis database. That goes off and accesses the MUTEX. Very simply, you move an address to the long word of the MUTEX data structure. You want to use the G-hat because you're in system space. You want to make sure that you're referencing it by the absolute indexing, absolute addressing. I'm going to pull myself down. I don't have that much tail here. Move that into R0, and then do a JSP into locked wait. In this case, I wanted to assert that I want write access to the data structures. In this case, the data structure is controlled by CIA$GQ_intruder, which is the queue head to a CIA data structures. Since it is a queue, and it is a doubly linked queue, as most of the ones in VMS, I just loaded the values of the queue header and the first address of the first element in the queue into R3 and R4, so I can do those comparisons and registers to make sure that I'm not trying to loop back to the queue head. If I go through with an empty queue, I'll bomb out immediately, and as I loop through it, I'll make sure that I'm not at the end of the queue. At the very end, move the address long word of the MUTEX data structure into R0 and call JSP $unlock. And my MUTEX will be released, and whoever else wants the MUTEX at that time, if anybody else, will have it. What will end up happening at the unlock is that the system will go through and check for anybody else that has that MUTEX address stored in their event flag wait mask that is currently sitting on the MWait process state queue. There's a queue of processes that are in MWait state, the MUTEX wait state, and it will just scan that list of PCBs that are stored in that queue to see who wants that lock next, if anyone. Resource waits are a little bit different. Resource waits are more related to an individual process. MUTEXs are more gaining access to system-wide resources at low IPL. Resource waits are typically a process quota or some sort of process-related event or construct that we're trying to allocate and want to guard against over-allocation of that. Some of those will impact some of the system data structures, which is why they're quoted and everything, to make sure that you don't go off and swamp the system. The process is still put into an MWait state, and if you decode the PCB state field, it will still show MWait. SDA and most of the other tools are very nice to actually realize that it is not in a MUTEX state, but it is actually in a resource wait, and we'll put a RW and then some mnemonic next to it telling you what resource wait it's specifically waiting for. Some of this has gone into in the Book of Ruth, chapter 12, page 283. You can disallow putting a process into a resource wait. By default, it usually is allowed by using the set resource wait system service. Note that this will not work for every resource wait. Some resource waits will not be affected by this because they depend on other things that are not necessarily directly quota related. These are mainly things such as an IO rundown that has not occurred yet, or awaiting the deletion of a sub-process. Processes in the resource wait are identified with a RW, typically as the first two letters of the process state. Here's a list of some of the resource waits that are used. There's several others that are defined, but a lot of them aren't used anymore. Of course, the number one on the top 10 list of resource waits is resource wait AST. That's the one that everyone seems to enjoy the most. Other ones you'll see is RWMBX for resource wait for mailbox. Typically means that a mailbox is full. If you do have this, there's ways to get around this. When you declare the mailbox, you may want to increase the mailbox buffer quo and max message count. This can allow you to put more messages and larger messages into the mailbox without getting a RWMBX state. Other ones you may see, I hope not, are non-page dynamic memory and page dynamic memory. That's typically meaning that your system's about ready to hang up because you can't get the memory you need. An interesting one is a modified page list empty. This is one you'll probably never see unless you're analyzing crash dumps. Modified page list empty is used by the OPC crash program, the last program that the system ever runs in its lifetime when it's getting ready to go down. to assert that I want the wait and put myself in a resource wait for the modified page list to empty. This wakes up the swapper and lets it know that somebody is waiting to flush the modified list, which guarantees all caches, all buffers, all writable data structures are flushed to disk before the system goes down. So that way you don't lose any data when the system goes down. Also, RWMPB, Patrick O'Malley likes to call this, really wanted my process back. And boy, that's the truth. If you have a modified page list, which is too small, MPW_high limit, you can raise that along with a high or wait limit in order to give yourself more modified page list. If your modified page list is too small, you'll start to see some or several processes go into this state, and what that is signifying is that we have to sit around and take your program, set it on a shelf while we take memory and write it to disk, so that then when we do that, we can wake you up and you can read that same memory back off disk again. Why do that? Boost up the modified page list, modified page writer high limits to see if you can avoid that. One that was seen especially in version 4 of early versions of VMS before 5.5 is RWSCS. RWSCS is System Communication Services, and there are certain buffers and quotas associated with two members of a cluster or more talking with each other, and Job Controller was a real good one for going into this state a lot if you had a lot of queues with lots of print and batch going on actively. One way to reduce the occurrences of this, if you do see this on a consistent basis, is a sysgem parameter called SCS buff count. SCS buff count controls the number of SCS buffers that are available and allows more cluster communication to kind of go through. RWCAP is for capacity if you have vector processors. Another one is RWSCV, which is the cluster server process. Whenever you do a cluster-wide process service call, such as the process, some of the process calls that go across a cluster, all this goes on through the CSP process. If the CSP process, since it is more single-threaded, is busy, what you will end up is getting several processes in this. Probably what you need to do is reduce the occurrences of people doing get GPI type calls or otherwise that are doing all the way across cluster type look-aheads. Resource wait is entered by using the $RWait routine within the executive, and you pass it the RSN $_ symbol that was in that previous list to tell it which resource wait that you wish the process to go into. The different parts of the executive will have the process go into different wait states depending on what it is. You can also, if you want to, in your programming some stuff, put your own process into a wait state and wait for it to come out at some later time. When the system goes into the RWait state, it goes into it immediately. It's not like a MUTEX where you jump into the SCED lock, and if the MUTEX is currently guarded, you go into an MWait right then. RWait is a directive. Yes, I want to go into RWait. I have checked the reasons that I want to go in there, and I definitely do want to go in there. And once you go in there, you don't actually come out until you get some sort of access through what's known as report system event, saying that you have an event that has occurred that may allow you to come out of that RWait. You then recheck to see what your cases are and then go back into RWait again. I'll show an example of that later. Whenever you set an RWait inside the SCH$GL_RESMASK, a bit is set system-wide stating which resource waits are currently being waited on. When the system RSE routine is called, report system event, and indicating that this process now has freed up an AST wait case or some other case, the scan is made of the current MWait processes to see which ones could possibly be waiting for that same resource. Those processes are then scheduled again so that they can go off and double check to make sure that the processes can get the quota or whatever caused the wait state has been resolved and they can come back again. Yeah, you got that. Here's an example you might see in various pieces of the executive of getting a process into a wait state. Go off and allocate, byte count allocate. We want to allocate some byte limit, but we also want to make sure that our process quota or our job quota inside our JIB is debited with that amount of quota, because this is a pooled quota across all our processes. We need to do that as a separate routine because of the way SMP is working. They have a special routine for that, so it will deduct the amount and also make sure that is properly deducted in the quotas, and you get your pool in one action, because there is actually a MUTEX on your own process JIP. And so you may end up going to MUTEX to do that routine as well. In this case, we're going to fail. Bit clear, we didn't have enough memory, so we move reason, page down memory. We didn't have enough page down in order to do this, and we'll put ourselves into that resource wait state. Then we do the JSV into SCED wait in order to assert that we want to go into a resource wait state. Once memory has been freed up into the non-page pool, our process will actually get woken up again. So in this case, we just loop back and try to reallocate the memory again. We have to actually remake that test, because just because we came out of the R-wait doesn't mean that the situation has been resolved. It just means that it's possibly been resolved. Once it's been allocated, we can go through and play with our new memory store. Okay, the one you've all been waiting for, R-waste specifically. R-waste, even though I really think it stands for really will annoy system types, stands for resource wait for an AST related event. Could be any AST related event. Since ASTs are so common throughout VMS, it could be I/O completions, it could be a sub-process completing, it could be about anything. Generally, why you're going to see a process fall into R-waste is for one of the following reasons. Process is waiting for deletion of a sub-process. If you actually do go off and are real quick on the keyboard, you can do a spawn, kill the parent process of that spawned process, and if you do a show system real quick, you'll actually see that parent process go into R-waste as it is waiting for its child process to be delivered a deletion, a del proc itself, go away, clean up, return all its pools and quotas and things like that to the job pool quotas, and then the parent process will actually go off and complete deleting itself. Other ones are AST, direct I/O limit, and buffered I/O limits being exceeded. Those are also very common, especially if you're using those limits as flow control. What will end up happening is, as I do 50 ASTs, there's also a couple of other ones in there as well, but those are the three big ones. As I exhaust that quota, I get put into the RWAST mode just to make sure that I get kind of set up on the shelf until some event, a lock completing, an I/O completing, frees up whatever resource I'm waiting for. The one that gets most people, though, that I've noticed, is the process waiting for an outstanding I/O. There are a few cases throughout the life of a system where a process will go off and do an I/O on a tape device, on a disk device, or a variety of other devices. And for whatever reason, that I/O will never complete, either probably because of a bug in a driver or a few other sets of strange circumstances. That I/O just doesn't complete. A process is not allowed to go away unless all its I/O counts are reset to 0 and all its I/O is completed. This makes sure that the system doesn't corrupt itself by trying to load memory into a process slot that no longer exists and corrupting someone else's memory, and a lot of the other ramifications of DMA. You have to make sure that all your data structures related to that I/O are cleaned up before you actually kill the process completely. Quota exhaustion, like it says here, is usually transient. Big ones are waiting for the I/O. Now sometimes you'll see the parent process go into R-waste, and a lot of times it's in R-waste because its sub-process is the one that's really in R-waste, and the two relate on each other. I've also seen some cases where locks will sometimes cascade in an R-waste state because you're waiting on one R-waste process and you have all these lock conditions that can't be satisfied as well. Your big tool for looking at this is SDA, the System Dump Analyzer. The one tool that goes and lets you look into anything you want to within a VMS on a running system. If the state name is MWait, then the process is in a MUTEX. If it's in a MUTEX and you want to find out what MUTEX it is, the easiest way to do it is to do an evaluate/address and then specify the number that is in the event flag wait mask data cell in the PCB. So if you do a show process and look at the event flag wait mask, it will probably be 8 some big number. Evaluate/address on that value will give you what that current MUTEX that is waiting on. Not in all cases. There's a few MUTEXs that float around the system, such as JIB MUTEXs, line printer MUTEXs, and a few others, and those that won't be able to resolve an address for, so you can't do too much about that unless you want to go through and figure out where that address resolves in the operating system. The two main commands you want to use are show process and show process/channel. Show process will give you a kind of a quick view of the process and its current quotas, and also how much quota has been used. That gives you an indication of whether you're dealing with a quota problem or some other problem. If you do have outstanding I/O, there'll be some I/O counts that are non-zero or that are non-equal to their quotas. And in that case, you want to do a show process/channel. Show process/channel will scan the process's current channel list and show you what channels it has active. Inside the channel control block is a bit that states whether or not, or is a flag saying how many I/Os are on this channel. And that flag there, well, its flag is busy if the process has active I/O. That's typically the device you need to go off and clear off. Here is an SDA output for a process I ran that I explicitly got it stuck into an R-waste mode. Did a show process/index equal OCF. OCF happened to be the process index if you need a list of what the process is. The index you can actually put in, say, the last 3 or 4 digits of the PID. The last 3 or 4 digits of the PID, depending on how the system is booted, will actually be the index value. Also, show summary in SDA will give you a listing of all processes on the system by PID and by index, and you can use the index value in that. The display gives you the name, addresses of various data structures, PCB, JIB, process header. The important flags, though, are event flag wait mask, which if you're in an MWait or an RW state, will tell you what you're waiting for. In this case, it's a 1. Remember on the previous chart, 1 was equal to RWAST. And sure enough, the RWAST is as noted as the state. Looking at the quotas, our ASTs are enabled, no ASTs are active. We have 148 ASTs, which is our AST limb, remaining, no problems there. Our buffered I/O count and limit. The count and limit aren't necessarily the actual count of current ones, but it's a deductible quota. So if it shows, I'm going to kill myself. If it shows a 0, what that means is you have 0 left. If you have 0 left, you're probably trying to do that -1 and it won't work. There's not too much quota evaluated off that. So in this case, it looks like we're definitely stuck on buffered I/O. Since we're doing, in this particular program, it's doing access on a mailbox, and mailboxes are buffered I/O, this makes perfect sense. So obviously we're stuck on some I/O because we have some non-zero I/O buffers here. So the show process/channel is our next step. In this case, we have MBA50, which is flagged as busy. So somehow we need to find out how to flush out this particular device. Mailboxes are fairly easy to flush out, and we'll go into that as we follow on here. Most of your undeletable processes, you try to do a stop/ID on them and they just decide to sit there and laugh at you. Sometimes they're in a local event flag state and they laugh at you by suddenly deciding they're going to stay in R-waste. Most of the time, almost all the time, it's caused by some uncompleted I/O. Some I/O that didn't get itself resolved, didn't back out, something just didn't happen to make it complete. So those are the ones we need to get rid of for getting them out. Some devices you can use some techniques, other ones you got to go off and do things completely different, and even go off and toggle on different subsystems within the operating system to get rid of them. Typically they resolve around a network device, mailboxes, disks and tapes, and yes, I've even seen it with printers. Network devices are generally pretty easy. The most common one of this one that I've seen is somebody has set host from one node to another. For some reason they have dropped their session, but the network and the RT terminal driver haven't quite figured out that the guy's no longer home. What will end up happening is that the DCL or whatever application is running in that remote process is trying to do I/O to its RT terminal, which hangs. And it gets itself stuck in an R-waste state. All we have to do in this case is, instead of killing the link from the RT side, we'll go into the back door and kill it from the DECnet NCP side. Generally, this is done by doing an NCP show known links. This will give you a list of all current DECnet links on the system. Once you have a list of those links, look for the one that is for processes called REMACP with the proper remote user, and then you can disconnect that link number. What will end up happening is that DECnet will assert that that link is down, It'll close this side. Probably the remote side's been killed already. We just need to make sure we get the local side done. And it'll also flag to the RT driver to signal a hang up to the process, which will complete the IOs. At that point, the process will finally go away and release whatever resources it had. Mailboxes are also another common one. And these are also pretty easy to get out of. Like on the display I had on the SDA, MBA50 was the target mailbox. Typically what you can do is copy the name of the mailbox to the null device, essentially try to take all the data that's in the mailbox and pull it out. That will free up someone that's trying to put messages into a mailbox, so they get rid of the RWMBX, and it also can get rid of some of the RWAST causes and free up that mailbox from whatever's causing it to be stalled out. Then, if that doesn't work, probably somebody's trying to run down an I/O reading the mailbox. So you can do something such as copy your login.com or whatever into the mailbox. You can also do this with the DCL commands, open, read, and write, and close with DCL. I would not do that because if you do manage to get that process stuck, it'll R-waste too. The best way to do it is with like a copy command or something that you can interrupt with a control Y more conveniently. DCL does not always control Y itself very well. Also, I'd suggest copying from the mailbox before you copy to the mailbox, just to make sure that the mailbox is flushed before you try to start dumping stuff into it. Tape devices are always interesting. A lot of times what happens is the tape device will fall offline for some whatever reason. Operator bumps into the cabinet or something like that, and doesn't always reinsert itself back online correctly. A lot of times what you can do is just to reload the tape and turn it back online. This will sometimes get the driver and the mount verify code to reestablish itself. Dismount/abort on the tape drive in order to try to clear the I/O and abort any outstanding I/Os. Sometimes the drivers will respond to that very well. One that I end up having to use several times, I've done this by inserting a TK50 tape into the TK70 console of a 6000. I forgot what kind of tape it was. It won't work. I initialized it, my process on the console, immediately went into R-waste, and I couldn't get the tape out of the drive. Well, here I am with the console locked up. My process is dead. I got a tape stuck in the drive. It won't come out. I can't turn the machine off. Everyone would get a little upset about that. The driver didn't know how to handle the situation, so the mount verify code kind of died in the driver. So what I had to do is to force it to pack acknowledge. PACAC is a function call you can make to the driver, and that's the call that's made actually during a mount operation. The mount verify code does not always seem to do this correctly or at the right times, or it times out or whatever, so sometimes you have to kind of jiggle it manually and make it happen. Very easy to do, small program. Just write this one is in macro. You could do it in another language if you wanted to just an ASCII descriptor of the device, such as MUA0. It's not focused. That's a little better. My contacts must be fuzzy too. Assign a channel and do a simple QIO with the PACAC modifier for the function. And that asserts a PAC acknowledge. A lot of times the mount verify code will properly reset itself and be able to I could take the tape out of the drive again. But of course, since I didn't know what I did, I tried to initialize it again, so I had to PAC acknowledge the drive again. This does require physical I/O privilege, and if the drive is shared or is currently in use by another process, may require the share privilege. But if you're running around trying to get processes out of R-waste, you're probably already privileged, so this probably isn't a big issue. But it does require physical I/O and possibly share system privileges. Actually, disks are very similar. A lot of times, dismount/abort, you want to specify /override equal checks. Otherwise, you will not get a dismount abort. It'll fail because there are currently files open on the volume. So you have to specify override equal checks. Again, toggling the drive on and offline, getting the hardware to try to signalize the drive is on and offline. And yes, also the PAC acknowledge routine. Instead of specifying a tape drive, put the disk drive name in there to assert that the drive is PAC acknowledged. A lot of times this will get the drives back online again. The one that just really dismayed me was line printers. I like to call it a perverse case because in the one I had it was. They're easy, close the doors, give it paper, do something, it's probably complaining about it. The first time I found one of these was we had a printer symbiont on a printer get itself an R waste. The printer had printed off half a line and jammed. So the printer I/O for the LP11 driver couldn't complete the I/O. The process just happened to have a lock taken out against the rights list data file for a higher level access. And of course, RMS doesn't like to drop access unless somebody else wants access. And then just about that time, an operator did a stop/next on the queue. So the process was told to delete itself. Well, the first thing that the system does is when it's going through deletion is it tries to deassign the channels. Well, it couldn't. We had an outstanding I/O. Well, we'll go into R-wait. Gee, we would like it if you would drop your locks first. But no, it didn't do that. The channels were not in that order. So we had a lock on a process that it could not free up because it could not gain access to its blocking AST in executive mode. And somebody else tried to access the rights list file. Well, they locked up waiting for the lock that the symbiont had. Well, since they locked up, the next person that tried to log in locked up, trying to access the rights list file. Somebody did a dir/owner, and instead of getting the owner field of the first file, they got locked up. We had a cluster with 600 people on about 8 nodes, all locked up because of a printer stall. Fortunately, the node I was on at the time, I could chase down the locks and figure out it was a symbiont and found out it was an R waste and went into the computer room to find out what it was. It was a stupid big washing machine LP27 with its door wide open, and I just reached over and closed the door. And 600 users were very grateful. This is one of the fun ones that I just love when they happen at 4:45 on a Friday afternoon, and you don't want to have to mess with this sort of stuff. Well, if those techniques don't work, reboot the system. Well, no, actually there's some other stuff you can do. The best one is to get the process control block address of the target process you want, assert SSR wait into the bit in the PCB under PCB status field, telling it that you do not want to do system service waits, and then clear the delete pending bit. This will allow you to send another del proc to the process, which actually is an AST to the process that it can respond to and loop back through this code again. And then you issue the del proc to the process to kill it. Now for those that just don't happen to know how to write the code off the top of their head, here is the first half of the code. I just created an ASCII descriptor for an 8-character PID. This is the binary value that the PID is once we figure out what it is, a prompt string, and we use $get foreign to get the PID from the command line. Once we do that, we call the OTS library to convert from a text hex into, ooh, that's fuzzy. Nah. Text hex into a long word, and if you have a problem with it, we'll bail out. Then we change mode to kernel to do it. Yes, this requires change mode to kernel, the evil priv, but that's okay, we can all live. We just take the binary PCB, load it at R0. JSB to EXE $EPID to PCB. What this will actually do is return a couple of other things, but the main thing is take the extended PID, which is shown by shown system or some of the other routines, and give us back into R0 the address of the PCB of the process. From there, BISL2 and BICL2 will set the wait flag, and it will clear the del pend, and then from kernel, what the heck, we can go ahead and issue another del proc from there. It's safe to do that. In case we do not get the proper PCB, we error out with a non-existent process just to make sure we don't try to set bits that are not necessarily in a good place. We'd hate to crash the machine. But that would clear the R wait. That would clear the R waste case. Now if there's any questions, or actually if anyone has any answers, that'd be good too. Take some of them. Yes. For those that missed it in the first half, if you want to be really cheap and not buy the big packet of session notes or even the single session notes, even from my session, I've set up a file server on my machine so you can do a send me r wasted, and it will send you a PostScript copy of these session notes, And you can also, while you're at it, get these session notes and beat the rush for my loadable executive images, which is tomorrow. I believe it, I don't have the SAG with me right now, but it is tomorrow in the ballroom 4, I believe at 3 o'clock. And of course, help or list if you don't know how to use a file server. Any questions? Oh, everyone understands this. That's such a joy. Everyone's ready to go off and kill off our wasted processes without crashing their machines and make their bosses really happy, I can tell. Microphone. Standard DECUS protocol, go to the microphone, name and affiliation, and then it will answer your question.
Charlie Hitzelberger, Nationwide Credit Corporation. So what would I do then? Would I just write a program like force exit and throw it in my utility directory? Or, you know, process nuker that does the thing in the last part?
Yes, you could take this code and put it up in and create it as a utility to help kill an R wasted process. Note that this will only really clear a lot of the resource quota issues. If the process does have an outstanding I/O against it, that program will not clear it out really. In that case, you have to go off, find out what the I/O is stalled against, and jiggle the device, kick the machine, do something in order to get that I/O to complete. And that's mainly using SDA, show process / channels. You also want to make sure, it's kind of a good idea to make sure you don't have a problem with the cascading lock issues, such as I had with the printer symbiont, because what can happen is if you do a show process / channels, it will try to give you the file name of the file if it is on a disk, and if that disk has a cascading lock on it, similar like the rights list file, you'll end up locking up your SDA session as well, because it's going to go off and talk to the XQP to try to find out what the name of the file is, and the XQPs are locked out from its locks as well. So make sure you don't have cascading locks. But a lot of times you don't. Most of the time you don't have RMS involved at that point. Any other questions? Great, everyone's happy. I like it when a plan comes together. Thank you very much.